So before we actually look into the algorithms, let's formalize what is the classifier, and then we'll look into some of the data structures and the mechanism to do this differentiated service or the packet classification. So we said that classifier is nothing but, or denoted with C, and nothing but a collection of the rules. Here in this case there are n rules, R1, R2 and Rn, and every rule has got things. One is called as the predicate. Rj is the rule, maybe Rj is the 10th rule, and this predicate is on every dimension, meaning the dimension source IP address is one dimension, destination IP address is another dimension. So you have a condition to evaluate on every dimension. Some of the dimensions you might have a wildcard like star, that is okay, but you have got a condition on every dimension. Star is also a condition, it is matching to every possibility, that is the difference. It has got a condition on the d dimensions, and then second thing what it has got is, it has got a priority assigned to this particular rule. We will come to that in a minute, why this priority is required, and then it has got a certain action to be performed. So a predicate, a combination of the predicates are there in the rule, and then an action to be taken, and then at the third point you have got a priority assigned to that particular rule. These three things are there, every rule has got this combination assigned to this. And a packet, we say that a packet P which is arriving at a router, let us say R1, a packet which is coming to this particular router, let me call that packet as P, and we pick up the header portion of that packet and extract the D attributes from that particular packet, and we say that a packet P actually match a rule Rj with the if all the D values, D1 to D2, D whatever dk you have, k number of the attributes or the dimensions, if all the k attributes match, then we say that this rule is actually matching. Now the question is whether there is only one rule that is matching or there can be more than one rule matching. So we will come back to that in a minute. So packet classification is all about given a packet P, extract D fields, do a matching, and if all the attributes that are required are matching in that particular rule for this packet, then we say that the packet is matched. And then it is not necessary that only one rule is matched, it is possible that more than one rule can match. So that is why we need to pick up a higher priority rule. If there are more than one matches, then you need to pick up the rule which is having the highest priority. Just an example, if the attributes are, let us say, source IP address and the destination IP address, and one rule says 10.10.1.1 and the destination IP address is, let us say, 2.2.2, this is the rule number 1, let me call it as R1, and the second rule R2 says that this is star, this is star. So it does not matter what is the source IP address and what is the destination IP address. So it is easy to note that R1 is actually a subset of R2. So R2 matches anything, does not matter what is the source and destination IP address, any packet that is coming to the router will be always find a match with the R2, but R1 is a set of that. Now the question is, if let us say R1 says you need to forward it with priority, R2 just say that you need to forward it. Whether I forward it with the priority or whether I forward it with the we just forward with normal priority, that is the differentiation we need to bring. That is actually resolved using the priority value. So that is why the packet classification problem is, you pick up a packet has arrived, you pick up the header values in that one, and you got a set of rules inside your classifier, evaluate against the rules inside your classifier and come back with the highest priority rule that is matching with this particular packet header fields. That is the classification problem. Now any classifier, any algorithm that I want to design need to do this kind of the operation. But the example just I gave you lead to something called as the rule conflict. So, the previous example that I took again on these two fields just to simplify the discussion. So, source IP address and destination IP address are the two fields. One is 10.10.1 and going to this 2.2.2. One is saying that you allow this communication, and the second one is saying irrespective of what is the source and destination IP address, you actually deny this communication happen. So, this is called, if let us say a packet comes P and the P has got the source IP address of 10.10.1.1 and the destination IP address of 2.2.2. Now, when I evaluate against these set of rules, both R1 and R2 match, and not to match, whether I am going to allow it or deny it. We said that we need to assign a priority to this rule. If R2 has got the highest priority, then you need to deny this particular packet to go through. If R1 has got the highest priority, then you should allow this particular packet to go through. Right. More the number of the fields that I got, higher the chance of this conflict. So, more than one rule might match, because for the same combination source and destination IP address, if I add protocol field, one with the TCP field, another with the UDP combination, I can have possibly two different rules inside my classifier. So, now as the combinations increase, the number of rules will also increase. The more the number of rules you have got inside your classifier, more the chances of the conflict. Now, in order to assign priority to the rules, I need to understand priority. How do I assign the priority to these rules? So, that brings us to the discussion something called as the conflict resolution. So, let us try to understand the rule conflicts are very much possible inside classifier, one telling something else, one telling something else, that's possible. So, now how do I actually resolve the conflict inside the rules? When I say the conflict resolution, basically I want to assign the priorities in such a manner that the conflict resolution is always possible. So, meaning can two different rules inside my classifier have the same priority? Maybe priority number 1 assigned to more than one number of the rules. If that is possible, again there might be conflicts. How do I actually resolve this conflict is the issue. So, let us try to understand that the strategies or different mechanisms used to resolve this conflict. So, there are 5 rules in this particular classifier, and the first one is saying 10.10.6, this is a class 16. So, IP address is falling in this range. Irrespective of what is the destination IP address, you should allow this particular packet to go through. So, again let us take the case that a particular packet comes with this combination 10.1.1. This is the source IP address and the destination IP address is, let us say again 2.2. Anyway, the rule R1 and R2 are the candidates now based on the source IP address, and the destination IP address combination for both the rules are stars. This is anyway going to match. R1 is going to match for this is the best case. And now you look into the other case. Now, R2 has got the source IP address. You see, this is not the prefix format, this is the entire IP address, and the other rule R1 is only the prefix format. Now, which rule to apply or which rule to prioritize? Maybe I am going to say that this has got the highest priority, maybe higher the number, higher the priority. You can have the other way around as well, and this has got the priority number 9. So, now the highest priority rule for this combination is R2, and based on whatever it says deny, you actually deny the particular packet, this packet to go through. Now, the question is this the only way with which you assign the priority? More specific the rule, you apply that. That is one way of resolving the conflict. That is the way, what we call it as the best match that you got. So, one is in the prefix format there are many other combinations in this prefix format. 10.10/16, another 2 to the power of 16 combinations fall under this series. That is not the specific one. Rule R2 is telling the exact IP address, source IP address. So that is the best match that you can find. So now if you use this strategy, what it means is, my classifier, in order to do a packet classification or a decision on that particular packet, you need to start with the rule R1 and then go across the table and evaluate all possible applicable rules, find out that, and then you actually come back with the one which is actually the best double one. So there could be many other possibilities. You can very well have another rule saying 10.10.10/24 in the prefix format. Now there will be not only 2, there will be 3 rules which are matching to this particular combination. So among all of them, you need to find out the best is. The second way to resolve this conflict is something called as the first match. What it means is, there are some rules inside my classifier and I am going one after the other, rule R1, R2, R3. You first apply the rule, whatever the rule which is applicable in the sequence, first one, you take the decision on that one. In this case, it also happens that if you get this particular packet, rule R1 is the first match. Using that, it is saying allow, you actually allow this. Now, if you follow the first match category, what it requires is, I want R2, because R2 is the more specific rule applicable to this particular combination, R2 to come ahead of the R1. So, maybe the order of these rules need to interchange, so that I can make the decision based on the remember, the routing or the forwarding is also happening using the longest prefix. So, same kind of the rule can also be applied here as well. So, R2 is more specific, I want that to apply. I want to, if you use the first match category, by default the rules inside the classifier need to be ordered in the decreasing order of their parity. So, which is having 10, R2 is having a parity, that should come first and then should come the R1. That is the another strategy that you can use. And the third strategy that you want to use is, if some rule is saying you need to deny or drop the packet, you go with this one, because denying or dropping is more conservative in nature, particularly if you are implementing firewall kind of the operation, some 2 systems you don't want to communicate. So, in this case, the rule R2 says the that has got the that is the best or match that you can find. Although this has got the lower priority, let us say the priority of this rule is 8 and the priority of rule R1 is 9 and the highest priority rule is the R1, but because R2 says you need to drop this particular packet, and dropping is more conservative in nature and it is best for the security. So, we want to apply that rule, whichever is saying you drop the packet. So, I am going to again look into the classifier, all the rules, and then find out all the applicable rules, and again start using the priority, and among them, if some rule is actually saying that you need to deny this particular packet, you apply that rule to that particular packet. This is how the evaluation is done. One is the best match, that requires, if your rules are not ordered, you need to traverse the entire set and then you come back with the best match that is possible with the highest priority. Second one is, if I have the ordered rules inside my classifier, you find out the first match, whatever is rule is applicable, then you forward or apply the action that is specified by that rule. And the third one is, you give priority to that rule which is actually denying the content. So, this is actually facilitating this kind of the operation is not an easy job, because you may have thousands of rules, and I can constantly keep inserting the new rules inside my classifier. Then if I insert one rule, that might conflict with so many other rules. I need to reorder the rules inside my classifier. What is the best order? or see, many things can get disturbed. Or if a rule is exited, taken out from this one, again you need to find out, re-alter the table, and all this can happen. Now we'll try to understand how exactly this kind of the rule matching and the action, applied action can be taken on that particular packet when you want to do the differentiated service. So another challenge is when whatever the rules that we saw in the previous case didn't have the, or the rules are specified in this particular format. Either there is a wildcard or there is a number, but that may not be the always the case. So what is the challenge here is sometimes the rules might not necessarily have the exact numbers, but a particular range. For example, rule R1 has got this source port in the range 1 to 10, and rule R4 similarly has got a range 1000 to 2000 in the source port format, and similarly for the destination port 25 to 35. Now how do we actually wait? It is not only one port. If I have to do a matching, I need to check whether the source port number in that particular packet is falling in this particular bracket or not. Now if I want to do a quick lookup or the matching of these rules, this is similar to that of the IP lookup table. And what we understood in the IP lookup table is, if the rules or the condition, the dimensions are specified or can be expressed in the form of a prefix. So in this case, this rule for the source IP address can be expressed as 10.10. Doesn't matter what is the next combination, that's the source IP address, and then 20.20. So this is in the prefix notation. I can always convert it into binary. Maybe if I convert this into binary, you will get this 000 and 1010. That is the first 8 bit, and then second 8 bit 000, and then 1010, and then you put a star. That is the prefix for this particular source IP address field in the rule R1. Similarly for R2 and R3 and so forth, and similarly for the destination IP field also, you can have this version happening. So the source and destination IP addresses can be expressed in the form of the prefixes, but not the source port number, destination port number, which is expressed in the form of the series in this range. How do I convert the port number, sequence of port numbers that are expressed here 1 to 10 into a prefix format? Prefix format, remember that if it is an exact IP address or the exact number, that can be a prefix format. For example, if source port number is 10, what is the prefix notation for this in binary? 1010 is the notation. So I can say that the prefix notation is 1010. This is the exact match. It's fine. So now it is not only one, there are 10 different IP addresses in this IP address field. How do I actually convert this into prefix format? Remember the data structure that we studied, maybe the Trie one or the hardware implementation that we studied for the route lookup are all applicable or efficient when the fields or the constraints or the predicates are expressed in the form of the prefix notation. So the one way to do this is take the rule R1, and the source port is actually expressing a range, and for every possible source port number you write a rule, meaning rule R1 is broken up, and for every source port value there will be one rule inserted into this classifier. So the same IP address, source IP address, destination IP address, protocol field, source IP address, when it is 1, you insert a rule 1. When the same source, destination IP address and the protocol field, when the port number is 2, and you have a second rule. Like this, one rule. Now because there are 10 source possible port numbers, there will be 10 different rules written inside the classifier. And it is no secret that if I do that, then the number of the rules inside the classifier would going to increase. They will be blown up. Now more the number of the rules you have in the classifier, more the work you need to do, because your number of the combinations. I don't know whether R1 match, R2 match, R2 match, n number of the rules are there. You need to evaluate all of them. So that is actually desirable. Now the question is there another way of doing this? Can I express the port numbers written inside this range format into a prefix format? There is a way to do that. We will come back and learn that part later. So, but assuming that is a challenge, and the set of the algorithm, the reason why I am talking about this right now is the set of the data structure that we are going to study are efficient for the prefix notation. So, if I use the prefix notation to express the all particular combinations of the values inside my rule, then I can implement the evaluation part quite efficiently. With that background, we will come back and see how to convert this range into a prefix format sometime later, but assuming it is there, then we will try to do that. Now, assume I have done all this, all my constraints are specified in terms of the prefix notation. Now, what are the practical requirements? What is the, how do I evaluate the performance of the one particular kind of the implementation? What are the advantages of particular implementation? One is the search speed, how much time it takes. Of course, when you want to do a matching over a set of rules, how much time it takes. More the number of rules you have got, more time it might take. The efficiency or the speed with which you want to do this matching will happen. So, if you have a 10 Gbps link, then approximately 32.2 million packets per second, that is the speed with which I want to do the classification. That is a practical requirement. And then second thing is, how much storage do I require to do this kind of the classification? If I come up with a data structure and if it is taking too much amount of the space, then that is not desirable. So, the efficiency of the storage of that data structure itself becomes an important parameter for making the decision. And can the data structure or the algorithm that I use can accommodate more number of the rules? Today I have got 100 rules, tomorrow I might have another 100 rules, and sometime down the line I might have thousands of rules. So, can the data structure scale well to accommodate new rules to be inserted in the table? How much change that I need to bring inside whether it requires the complete rearrangement or rebuilding from the scratch, or can I build incrementally, alter the data structure and accommodate new rules? Whether that flexibility is there, that is another requirement. It need to be flexible to accommodate that. And today I have got D number of the rules, maybe D is equal to 5 fields today. Tomorrow my dimension might increase to 10. Can the data structure accommodate that increased number of the fields, header fields? And then the fifth parameter is how much time it takes to do the update operation, whether it is I can do it quickly, maybe a fraction of a millisecond, or it takes time, whether there is a downtime involved. I do the update, take out the old set of the rules and put the new set of the rules inside my router. If this requires the downtime of the router, that is not desirable. And last parameter is flexibility of the specification. As a user, I don't want, maybe if you go back to the previous example, the source IP address and destination IP address can be expressed in the form of the prefix. This is the source IP address and this is the destination IP address, but the port number need to be expressed in the form of the range. As a user, I specify in this range, then the router automatically takes this and then does whatever the format it want to convert it into automatically and then do it. So, that gives the ease of specification to the end user. If I am the network administrator, my job becomes easy. So, I can write minimal set of the rules and then whether it is replicating, creating multiple number of rules out of one, or converting the range into prefix format, whatever it is doing, let it do, the router automatically do. So, that kind of flexibility if the router provides, the better it is. So, Whether we want to, whether all of these can be met or not is a question, but at least in theory, these are the kind of the parameters we want to take into consideration when we want to implement or make choice of the one kind of data structure over the other one kind of the algorithm over the other one.